Hello, in this session I'm going to go over logistic regression. This presentation is partly based on a book from our library available online at this link, and also another book that I happen to have on multivariate data analysis. Logistic regression is similar to regression, but the idea here is we want to develop a relationship between independent variables and the dependent variable. But the thing is, the dependent variable is a binary variable. In a traditional regression, the dependent variable would be a continuous variable, whereas in logistic regression, the dependent variable is a binary variable, 0 or 1, as a value it can get. The quantitative relationship we will develop will help in determining if the probability of a dependent variable being 1. Since traditional regression or linear regression would try and predict a value for the dependent variable, here we will not predict whether the dependent variable will be 0 or 1, but we'll predict the probability of the dependent variable being 1. And there's lots of situations in data mining that can use logistic regression. Take this scenario of data. This is from the multivariate book I happen to have. Let's say we have data on individuals' income data, annual income in thousands of dollars, and also we have data on whether the person frequents restaurants. So if somebody who frequents restaurants is a lot of times, then we give value 1, otherwise value 0. Now what we want to find out is, from this data, we'd like to know what is the probability that someone whose income is $25,000 will frequent restaurants. Now from this data, how can you predict that? Now if you try and plot the data income in thousands on the x-axis and whether somebody frequents restaurants on the y-axis, it looks like that. It doesn't really show relationship, but just shows a bunch of points on the 0 line and a bunch of points on the 1 line, because that's the nature of the data. Now if you build a regression line for this, it may look something like this. Okay, and so as we'll see in a few minutes, if you do it in Excel, this is what you come up with. Now if you try and use this expression to predict, and if we'll predict y for x equals 25, y becomes 0.3838. Now that is of course not what we want. We'd like to know, because this one it'll have to be 0 or 1. Of course this is 0.3838. that is not what we want. And to understand how logistic regression works, we need to know about probability and odds ratio. A probability is, of course, it's if is assigned a value, any value from 0 to 1, and it's a probability of an event from occurring. The probability of event not occurring would be just a complement of that. That will be 1 minus p. So usually lowercase p is used to depict probability, and 1 minus p would be the probability of that event not occurring. Odds ratio is essentially the ratio of probability that an event occurs over the probability of event not occurring. So it's p over 1 minus p. And now this odds ratio usually is referred in terms of integers rather than fractions. So such as we say like 19 to 1, 20 to 1, 50 to 1, and so on. Now of course this is a very kind of a bad odds ratio, 19 to 1. It's kind of a long shot at a racetrack. And so how is odds calculated? Probability of loss over probability of win. And if probability of loss is p, then 1 minus p over 1 minus p. Alright, now consider the case of a race. Suppose the probability of a horse named Sahara winning the race is 0.05. And this means the probability of Sahara not winning is 1 minus 0.05, which is 0.95. So odds ratio is it should be 0.05 over 0.95, which is 1 in 19. So this means Sahara has 1 chance of winning and 19 chances of losing. Okay, now so that's how we calculate odds ratio given probability. Okay, now odds ratio, it can go from 0, it can be a fraction, and can be any positive number. So the blue line here is odds ratio, but at the same time, if you take the log of what the odds ratio, then it'll go from negative infinity to positive infinity. Okay, just like any curve. And say if you have log of if log's odds ratio is 0, when the probability is 50%. So when it's 50, then it's 0.5 or 0.5. The odds ratio is 1, so log of 1 is 0, right? And so we would be using the log of odds ratio as the value, as a predictor value. Now I'm sort of jumping the gun, but what we want to try and find out is from this data, we would like to know if probability of frequenting restaurants, if the income is less than 25,000, then if you just purely look at the data, that if between 0 to 25 there are 9 observations. Of these 9 observations, only 2 observations are ones, so the probability is 0.22. And the probability of not frequenting is 1 minus 0.22 is 0.78. So odds ratio will be 0.28. Similarly, you can calculate probability of frequenting if the income is above 30,000, that's 0.9, and probability of not frequenting when you have income above 30,000 is 0.1. So odds ratio in this case would be 9 to 1. And so we can calculate odds ratio given any data set. This odds ratio is the basis for a logistic regression, and but we'll be handling using log of odds ratio. And then we can once we have the log of odds ratio, we can then convert it to probability using the logistic function. Okay. Now what we do is the solution to this problem is we want to come up with the prediction line. Simply we have only one independent variable, which is x1, which is our income level, and the dependent variable on the left side is the log of odds ratio of somebody frequenting restaurant or not. Now how do we figure out this? So what we do is it's not a straightforward regression, but we'll assume we have an intercept 0 and slope beta 1, and for any starting value we'll compute the logit values, which is nothing but this left hand side expression here, and then we take the exponential of the logits, that becomes our odds ratio. Then we convert the odds ratio to probability p for value s or 1, for s, probability p for value yes or value 1 for each record. Then we either use p or 1 minus p. Then we take a product of all the probabilities, and then we take the log of that probability of that product of the probabilities. Then we maximize a log likelihood value, that's called log likelihood value. We maximize it by manipulating the coefficients. Okay, now how is that done? I can demonstrate that using Excel. So let's switch to Excel just for 1 minute. Okay, here I'm in Excel, and okay, here's my original data. That's an independent variable. Here's a dependent variable, and here are my two coefficients, the intercept and the coefficient. Right now I don't know what they are. Just set it to 1. Then I calculate the logarithmic unit, which is simply using this formula. Using this formula, I calculate the left hand side, which is intercept plus independent variable times the coefficient. Then for this value, I take the exponential of that. That's my odds ratio. Then from this value, I compute the probability. So odds ratio over 1 plus odds ratio gives me the probability. And based on if the actual value is 0, then I take 1 minus this probability. Otherwise, I use the value itself. Now I have to calculate, this is called the log likelihood value, and I have to calculate all this for all the observations. So I calculate this for all the observations. This is what it ends up to be. Then what I have to do is I have to take all these log likelihood values and multiply them, all of them. Take a product of all those numbers. Now fortunately in Excel we have a function for that. It's called product. So product G3 to G22 will get me the product of all these numbers. Then I take the log of those products to get negative 212.5. Alright, so now that I have this number, I want to maximize this value by manipulating these two parts of the equation, right? So I use Excel solver, and a solver is a tool in Excel that lets you solve simple optimization problems. So data solver, and we want to set G25 to maximize by changing H2I2, and go ahead and click solve. And once you solve it, it will plug the value right inside your spreadsheet. You can keep solver solution, click OK, and there it is. So we have calculated the intercept and coefficient that maximizes the product of log likelihood values. And now this is the actual solution to the problem. Now based on this, we now have calculated probabilities. Very good. And now of course, if you want to try and plot this, you could do that. The plot is right here. So on the x-axis I have the income in thousands. On the y-axis I have the probability. So reading off of this, I can find out for x equals 25,000, probability will be the odds ratio is around 0.4, and then I can use that to calculate the probability. So coming back to our presentation, we apply this formula, that is probability equals 1 over 1 plus e to the negative logit p, and for the problem of this one, the problem with the logit equation figured out, we can calculate the probability as 0.351731. Alright, so that is the probability of somebody frequenting a restaurant when that person's income is 25,000. And we can calculate for any value of x, and so once you calculate for all the values of x, we have this, and the resulting logistic regression would look like this. Okay, the idea is to come up with sort of a S-shaped curve that gives you the odds ratio for that gives you the probability for any income. And so this is a kind of a background to logistic regression, and hopefully you found it useful. Thanks.